conferences. It was a real hectic event, real hectic effort. We were all running around, going to airport, bringing our guests, putting in hotel, this, that, then the caterer, whether they will send the food packet in time and whether the car rental agency will send the car in time. And it was really, really a headache. But now you can see that you assign some jobs to your colleagues and everybody is sitting there home and putting a curtain behind them so that the background looks good. And that's it, you know. So in a way, it has become simple. And for me, it is a little bit tedious because, you know, if you regularly sit in front of this, useless laptop and then just see faces on the screen and talk, to me, it is little bit of tedious and boring because I was at least just before he said that enjoyment does not mean that we will have only the evening dance or music, but meeting in the physical domain. But after 6 months, things have come to such a stage that it's mostly in the psychological domain now. But we have to live with it and we have to go through all this. And I am very happy that the entire team and all of them happen to be my colleagues and also my scholars. So I am really happy that you are taking all these initiatives and supported admirably well by our Kolkata section led by Mr. Kachudhuri and his team. So it's a very commendable initiative. And on behalf of, my personal behalf and on behalf of IEEE India Council, I congratulate the organizing team for bringing out the second version of this ASPCON. I will not talk about the technical aspects because I don't think today I am here to talk about anything about the technical part of the signal processing that people will do who know better than me. In fact, I can see Dr. Munshi, Professor Munshi very eagerly looking at the screen and so those people will talk about the technical aspects, and there are very eminent people I have seen. Of course, Professor Sanghamitra Bandyopadhyay is the icon of this conference, along with others, Bhaskar Rai Choudhury, and like those eminent people will be there. And but most importantly is that the participants. I wish that they will participate actively, but they will miss something that, you know, in a conference, these participants during lunchtime or any free time, they can sit together, 2, 3 people in a group and discuss their research and others. But that's the part missing in this online forum. But let us live with it and let us make the best possible use of whatever is available to us. And I am pretty sure that your team has made very good technical arrangements so that there will be no hitch. I know Sushanto will make a good job of that. Just 2, 3 days back, I was seeing him in a podium of another conference. Now, today, I don't think there is a podium. In fact, today morning, I was asking one of you, one of the organizers, that are you making any podium? And if yes, then I will go to the podium rather than sitting in my room. But then I knew that there is no podium today. But it would have been better. But I was told that there are certain technicalities. So anyway, all the best. Take care, all of you, not just the organizers, all the participants from all over India. I was going through the name. I have already seen the names of the participants. So all the best to all the participants. And I can only say that keep up the good work, raise the bar for the standard of your work. Don't lower the bar, raise the bar of the standard of the work. And keep the flag of IEEE flying very high. Thanks a lot for inviting me and very best wishes for ASPCON 2020.
Thank you, sir. Thank you for your nice words. Again, from our side, a small token of gratitude to Professor Shivaji Chakraborty. Uh, we'll definitely send this via email. So thank you, sir, for being here. I,
Okay,
I'd like
looks
to,
very nice.
okay, thank you, sir. I would like also to say that had it been a real conference, then high tension laboratory of electrical engineering department of Jadavpur University, Kolkata, India, would have been the local host. It is the local host of this conference. So, and you have got enormous support from the Department of Electrical Engineering for organizing this. So we had invited Professor Keshav Bhattacharya, who is the head of the department of the Electrical Engineering Department of Jadavpur University now, but due to his physical illness, he is unable to present here, but he just gave us the message and encouraged us for taking up this conference, and he also wished all success for this conference. So we also like to thank Professor Keshav Bhattacharya, though he is not present here. And also I can see in the audience our respected professors of the Department of Electrical Engineering, and also professors from other institutes and other departments are also here. So thank you, sir, for supporting us. And and now Professor Shugato Munshi is here. So sir, if you want to say a quick few words now, then you can say, because we are not having Professor Kisha Bhattacharya here. So if you want to say a few words about this conference, yeah.
Yes, a very good morning to all of you. Now, this is a conference on signal processing and applied signal processing. I have had a brush through the topics of the papers, and I have seen, starting from communication to illumination engineering, instrumentation, etc. A lot of papers have been submitted. Now, signal processing, as Mr. Karchaudhary has rightly pointed out, you cannot get rid of signal processing because it's there in everyday life. So that's the importance of signal processing to us, and particularly applied signal processing, because if you just dwell on theory and remain there, it's no use. Applied signal processing, therefore, is a very important aspect. And I had been there in the first edition of this conference, and this is the second edition. The first edition was a very successful one, and the second edition also, from the papers and from the speakers that who will be speaking, the eminent speakers. From that, I am also sure that this conference also be a very good, grand success. So I hope, I wish that this conference will be a very great success. And I just again convey my best wishes to all the participants, the organizers, the dignitaries present here, and be safe, stay well. Thank you.
Thank you, sir. Definitely, we'll be having more interaction with you in the coming sessions, as you are one of our invited speakers in this conference. So, thank you, sir. So, now it is time to the former lighting of the lamp to inaugurate the particular conference. So, with the permission of all the dignitaries and distinguished guests, I'd like to request our publication chair, Professor Vishendu Chatterjee, to please kindly help uh, to for lighting the lamp.
Where is he?
Okay, it will be seen. That, so we welcome you all with this. So formally, we can say the conference has started. I can see Professor Sanghamitra Bandyopadhyay has also joined. So thank you, madam, for joining. The next after this inaugural session, we have a keynote speech by Professor Sanghamitra Bandyopadhyay. But now we'd like to just take the permission of the dignitaries and our distinguished guests to just release our proceedings of ASPCON 2020, and that is also will be done virtually. And again, the publication chair, Professor Vishendu Chatterjee, will do the honors. And with the permission of all of you, all the participants, we have already distributed that, but to make a formality, we have just we have just created this password protected file. We have not given the password. Now after release of this, we are just giving the password to all the participants. So please start, release the proceedings. So we have released the proceedings of the ASPCON 2020, and with the clapping from all of you, and also the virtual clapping is also in the background. And with this, so we have to release the password also, and the password is given in the chat box also. It will be capital ASPCON and 2020 and last hash. It is ASPCON 2020 hash, capital ASPCON 2020 hash. So now the password is given to all the participants and they can now open the proceedings. So now we have come to the end of this inaugural session. So thank you for being with us, but I would like to request our conference organizing chair, Professor Shobhan Dalai, to give the formal vote of thanks.
A very good morning to all of you. Even though it is my duty to deliver the formal vote of thanks of this inaugural session of IEEE ASPCON 2020, it is known to all of us, especially for those who are involved in organizing such big events like ASPCON 2020, that such vote of thanks is always incomplete in the sense that it is impossible to mention the names of all the people who are directly and indirectly involved in making the event possible. There are always many unnamed people behind the curtain of such events. On behalf of organizing committee and also on my personal behalf, I would like to thank all the persons whose active support makes it possible to organize this conference. It is my great pleasure and honor to thank the dignitaries on the inaugural session, Professor Sivaji Chakraborty and Mr. Sanjay Chaudhary, for being present in this inaugural session and adding a glow to the conference. I would like to thank IEEE Kolkata section for their technical support. Department of Electrical Engineering, especially High Tension Laboratory, for being the local host of the conference. The main pillar of any successful conference is the participant. So I would like to express my heartiest thanks to each and every participant and of course author for supporting us and presenting their work in this conference. Now I would like to thank our respected teachers of our university and outside and colleagues for their advice, thoughts, and active support in organizing this event. I would like to thank the respected members of the advisory committee, technical program committee, and reviewers for taking the pain to organize the conference in a timely manner. This event would not have been possible without the untiring effort of our volunteer students for the last 1 year or so. I thank you all again for being an important integral part of this conference and giving us the opportunity to have the honor to have interaction with you. So this concludes the inaugural session, and now we are going to start the keynote lecture session of IEEE ASPCON 2020. The speaker of this session is Professor Sanghamitra Bandyopadhyay. Now I would like to request Professor Susanto Rai, the Technical Program Committee Chair of ASPCON 2020, to introduce the speaker to the audience. Thank you.
Thank you, Dr. Doloi. So good afternoon, ladies and gentlemen. It's a great pleasure for me to introduce Professor Sanghamitra Bandyopadhyay, who is going to talk about graphs, neural networks, computing and learning with graphs. Professor Bandyopadhyay joined the Machine Intelligence Unit of the Indian Statistical Institute as a faculty member in 1999 after completing her PhD from the same institute. She is currently the director of the institute and also HAG professor at Machine Intelligence Unit of the same institute. She has worked in various universities and institutes worldwide like USA, Australia, Germany, France, Italy, China, Slovenia, and Mexico, and also delivered invited lectures in many more countries. She has received several awards and fellowships, including Bhatnagar Prize, Infosys Award, TWAS Prize, DBT National Women Bioscientists, Young Award, ANAE Silver Jubilee Prize, Young Scientist Engineer Medals of INSA, INAE, and Science Congress, J.C. Bose Fellowship, Charno Jayanti Fellowship, and Humboldt Fellowship. She is the Senior Associate of ICTP and Fellow of INSA, INAE, NASI, and IEEE. She is currently a member of the Science, Technology and Innovation Advisory Council of Prime Minister of India. The current research interests of Professor Sanghamitra Bandyopadhyay include computational biology, bioinformatics, soft and evolutionary computation, pattern recognition, and data mining. She has authored and co-authored more than 300 research articles in the international journals, conferences, and book chapters. She has published 6 authored and edited books from publishers like Springer, World Scientific, and Wiley. She has also edited journal special issues in area of subcomputing, data mining, and bioinformatics. Now I would like to request Professor Sanghamitra Bandyopadhyay to take the charge of this session and enlighten us with your valuable lectures. Please, ma'am.
Am I audible?
Yes, ma'am, you are audible.
Yes,
Okay. So thank you very much. First of all, I would like to thank the organizers of ASPCON 2020 for inviting me to this conference and to deliver the keynote talk here. Let me just first try to share my screen. Just give me a moment, please.
Meanwhile, I would like to add that Madam has a very important meeting at Delhi, but still she has agreed to deliver the talk. After this talk, he has to run to catch the flight. So thank you, Madam, again on our behalf for agreeing within this tight schedule. You have agreed to deliver the talk. Thank you, Madam.
Thank you very much. My pleasure. But I'm just keeping my fingers crossed. From the morning, twice the power went off. So I hope it doesn't trouble now. Is the screen visible?
Yes,
Yes, ma'am, it is visible.
Yes.
And is it now full screen?
Yes.
Full screen.
Yes.
Okay, thank you very much. So I'll just, I think I have about half an hour. I'll try to restrict myself to the next 30 minutes. And this is a new topic that I'm actually trying to get into. And therefore, it has been a learning experience for me. And since it's rather new, I thought, why not talk about this particular area and in front of an August gathering, who, with their questions, might also force me to think something more in this particular domain. So I'll be speaking on graph neural networks, computing and learning with graphs. As has already been told, I'm Shanghamitra Bandopadhyay from the Indian Statistical Institute. And as you can see, there's a picture of ISI, the main building, in the background. So the question is, why do we need graphs? Because we are doing data analytics for a long time. And typically we work with data sets which are represented as matrices, as tables, and we have been doing fine. But graphs, as we all appreciate, as we all understand, are very powerful and a very generalized way of describing very complex relationships among objects, something which is very difficult to express in reasonably simple table form. For example, we have the social networks, we all know. It's a very complicated network, which you can see on the right-hand side, a very complex network. Biomedical networks, for example, networks operating inside the cells, between the molecules inside the cells. For example, it could be genes, interacting with proteins, it could be proteins interacting with proteins, it could be drugs, the medicines that we take, medicines interacting with other medicines, medicines interacting with their targets inside the cell, which typically are proteins. So there are different types of networks which are in operation in real life, citation networks, e-commerce networks, many more networks. And graphs are very powerful mechanisms of describing such complex systems. So that is why we do have to work with graphs. So what are the machine learning tasks and that we would typically like to do? I mentioned just a few here. For example, we would like to classify the nodes, predict the class of a node in a graph. The nodes may have some classes associated with them. Given a new node, we would like to classify which class this new node would belong to. Similarly, we may want to use the graphical structure to present links which we may not have experimented with. Maybe between X and Y, we have no link at the moment in the graph because we have not looked into this possibility. So looking at the entire graph and its topology, its structure, its properties, can we predict whether a link may exist between X and Y? Classifying the entire graphs is another problem. Graphs can be of different types. For example, a molecule can be represented as a graph, and let's say there are a million molecules. Some of these molecules are, let's say the classes, class 1 would mean that these molecules, they play important roles in a particular disease, and another set of molecules, they have no role to play in that disease. So the entire molecule is a graph. So this will be a million graphs, which with some class label associated with these small graphs, which are molecules. Each graph is a molecule. And we would like to learn how to predict the class. So now if a new molecule comes in, which is a new graph, can we predict the class of the graph? So this is another machine learning task which we may want to do on graphs. The question is, just to go through quickly, for example, we have a graph like this, where you can see different nodes A, B, C, D, E, and there are two classes, class 0 and class 1. And the task is, given the structure, if we have this unknown node here with unknown class label, can we predict what class it will belong to? That is the node classification problem. This is a link prediction problem. Suppose a new person joins a Facebook network. Can we predict which are the links this person is likely to establish so that we can recommend those links to him or her? So this is typically one example of link prediction. The other example of graph classification is something like this. Suppose we have graphs of these two types. This graph A is labeled class 0, this graph B is labeled class 1. We want to learn a function f such that it will take this graph as its parameter and it will give the output as 0, meaning that this class should, we have learned a function f which is able to distinguish between the classes of these two graphs. So this, it will take this graph, meaning this graph, as an input and will give an output of 1. So this is what we mean by the different machine learning tasks on graphs. Now the question is, why is it important? Why is it difficult? Because machine learning on graphs is more difficult than doing conventional machine learning on tabular data which is represented as matrices, rows and columns with fixed structure, or even doing machine learning with images or with sequences. Graphs, doing machine learning with graphs is slightly more difficult. Why is it so? Simply because graph data is, there's a high amount of variability in a graph. If we look at an image, for example, if we take a pixel, then we know that it has 8 neighbors. This is the top neighbor, this is the bottom neighbor, etc. So it's all fixed. Any internal pixel that you can think of, except the pixels on the edge, any internal pixel will have the same structure, 8 neighbors and so on. If we look at sequences, for example, suppose it's a sequence of, it's a video, so sequence of images, we know that the sequence has a particular meaning, something which is coming before one particular image is in time, temporally, just immediately preceding it and immediately following it. So the sequence would have a specific structure in the sense that there is an immediate predecessor and an immediate successor. But in graphs, as you can understand, this sort of definition is not possible, because graphs, each graph would have different, each node in a graph would have different number of different degrees, meaning it would have connections to different number of nodes. The number of nodes in a graph will be different from graph to graph. The structure is different, the labeling would be different. Edges may be labeled, may not be labeled, may be directed, may be undirected. So there are multiple meanings which you can associate with the nodes and with the edges. And in a given graph, not all nodes would be of uniform type, uniform character, or even uniform in the number of its connectivities, in the number of the links of the node. So it is all very dynamic, it is variable, and therefore the challenges are more. So this just shows a general machine learning life cycle where we have a raw data and we do some feature engineering to get a structured data, which is typically in the form of a table. We use a learning algorithm as a downstream task on this structured data, and then we learn a model of the data set. That model can help me predict the class of an unknown point. That model can help me tell that, okay, these are the points which are very similar to each other, or it may be a regression type of model which will give me some real values of an unknown feature vector, etc. When we go into deep learning, for example, then this feature engineering part is not really required anymore, because we don't have to extract features ourselves. Human intervention is removed, and the system itself implicitly will learn the features, and then the classification happens, or whatever machine learning task you want to do. But even that is difficult when the input is a graph, because simply because when if you think of convolutional neural networks, CNN, for example, then you will see that the kernel that you design, it has a specific shape, a specific structure, which is a 3x3 kernel. If it's an image, if the input is an image, it will be a 3x3 kernel. Or if the input is a sequence, it will be maybe x plus 1 and x minus 1. So minus 1, x minus 1, x and x plus 1. This will be your kernel. So it has a specific uniform meaning. It has a specific uniform operation. But for graph, this is very difficult to come up with a uniform kernel. So in graph, even this automatic learning of features, this becomes very difficult. So how do we handle such problems is what graph neural networks would do. As I must tell here that there's one one approach of doing analytics with graphs, which is purely in the graph theoretic framework. That is, there are graph algorithms which you can apply. This is a different approach for doing similar activities, similar functions. So what is done here is, given a graph, a feature vector is embedded, an embedding of the feature vectors, an embedding of the nodes in an Euclidean space is learned using some neural network, some learning algorithm. And then what happens is you have a set of feature vectors. Now you can apply your favorite machine learning task that you want to do. So the important thing here is, how do we learn the feature vectors? So given a graph, let's say it has 10 nodes. So what we have to do is we have to learn the embedding of these 10 nodes in an embedding in an Euclidean space, such that the embedded feature vectors, the feature vectors that now result for each of these nodes, they have a particular property, they have a particular characteristic. So essentially what happens is, after this graph neural network has completed its task, given a graph, you would now have a set of feature vectors. And this shows what I'm trying to say. Suppose it's a node classification problem, then what I have to learn from the graph is this function f, which given a node will give its d-dimensional embedding. Okay, so this is an embedding for, not for the graph, but for the nodes of the graph. So each node would now be associated with a d-dimensional encoding. Okay, so there would be an encoding here, a vector, a d-dimensional vector here, a d-dimensional vector here, a d-dimensional vector in all the nodes. The task is to learn this f, how to embed this particular node, or any node for that matter, into a d-dimensional Euclidean space, such that, you see, the property that has to be maintained is, if two nodes in a graph are close to each other in the original network, in the original space, in the original graph space, then their embeddings should be close to each other in the embedded space than, for example, the embedding of U and the embedding of, can you see the cursor for by the way, the cursor moving? Can you see it?
Yes, it is visible. Yes.
So given an embedding of U and an embedding of this node, maybe this node is embedded somewhere here, let's say, in this space somewhere here. So the distance between U and V should be smaller than the distance between U and the embedding of this node. Why? Because U is farther away from this particular node than U is from V. So this property has to be maintained in this embedding. And the task is to start with an initial embedding. It could be provided by the user, initial vector, and then learn the final vector through a series of steps where the information will be passed from its neighbors to this node. So not only will it compute with its own vector, but it will also, in steps, get information from its neighbors. And in the next step, this node has also done the similar thing, in the sense that this node has learned something from its own neighbors. So in the next step, what happens when this node has learned something from its neighbors? So in step number 2, this node will again get information from this particular neighbor, but now effectively it is also getting some information from here. So this is called k-hot learning, meaning in k steps, it will try to get information from its kth hop neighbor. So this is what is the philosophy of graph neural networks. This gives you just a timeline of how it has developed. It is not very old, I would say. 2008, this paper was published, and this is when it sort of came in for the first time. But then people were not interested. They were not looking into this particular approach of graph neural network. But since 2014, when social network analysis also gained in importance, then people started looking at this thing. And now thereafter, it has actually gained quite a bit of importance. Many people, many researchers are now using it. So I would say this is of the order of 6 to 7 years that is the age of this. Therefore, lot of work needs to be done. It's still an open area. A lot of contributions can come in. Therefore, a new researcher who is trying to get into machine learning may look at this sort of approach to do, because it is not that that much researched yet. A lot of work can be still done here. So how is this embedding happening? As I said, for this node, let's say I may want to start with its class itself as an embedding. So since this node has two classes, sorry, not this node, this graph has two classes, class 0 and class 1, I may decide that I will have a two-dimensional embedding. So this will be, it could be, let's say 0, 1 here as the initial, because if I say that the first vector is for the first class 1 and the next for the class 0, then I can appropriately start with an initial labeling of each node, meaning an initial vector associated with each node. Thereafter, through message passing, this node will pass its own embedding to this node. This node will pass, so this node will get embeddings from this node, this, and this, all its neighbors in the first step. But in the 0th step, it only starts with its own embedding, which is an initial embedding. Then what happens is, as the steps go further, this node, you will see that this is the circle, which was the 0th hot. Next, because it has first degree neighborhood with this, and this, these 4 nodes. So essentially, this big ellipse here is what is where this node, the node A, will get its inputs from in the second step, and this continues. But what happens when these nodes get inputs, get messages from their neighbors? What happens? Essentially, 2 things happen. So essentially, let me again go back a little. So what happens is, each node, a rooted subtree is considered at each node. For example, if you look here, if I go back to the graph here, A has neighborhoods from B, C, D, and E. So you can see here, A will get information from B, C, D, and E. And if we look further, B, because A was a neighbor of B, B is a neighbor of A, so B would get inputs from A, C would get input from A, F, G, D would get inputs from A, E, I, etc. And here we stopped building this rooted tree at level 2, because we have decided that we will go to 2 steps, 2 hops, no more than that. So what is done is, from here in the first step, each node has its initial embedding. So each node would have its initial embedding. Let's look at this. C has neighbors from A, F, and G. If you look at the original network, you will see C has neighbors from A, F, and G. So the initial embeddings from A, F, and G will be aggregated in some form, which is where the learning comes in. And then what will happen is, C will look at its own embedding and the aggregated embedding from AFG, which is the output of here, and it will do a combination. So it will combine its own embedding with the embeddings resulting after aggregating the embeddings of A, F, and G, and will come up with its own embedding. Similarly, B will come with its own embedding, C, D, and E. This is embedding after one iteration. And after the second iteration, the embeddings from B, C, D, and E will be aggregated here in some form. Again, a learning happens here. And then A will combine the output of this aggregated learned system with its own embedding and will update its own embedding. So this is how, in 2 shots, it will get its own embedding. Now, typical aggregating functions use something like this. For example, it could be like a rectified linear unit, which is like for negative values, it's all output is 0, and for positive values, the output is equal to the input value. That is what ReLU, the rectified linear output, is. So there is, you will see, I will not go into the details of this because it will take a little more time, but you can see a weight matrix here. And this weight matrix is what is learned. So that the loss function, meaning if it is a node classification problem, then the desired node classification and the node classification which is resulting from some W, some weight matrix, that difference is the loss function that is backpropagated or that is used for retraining, for adapting the weights. So this weight matrix is the learnable weight matrix. And max, here max is just max pooling. So this is how the aggregation of different, the inputs from different nodes may happen. And then a combined function, that is the node V. So essentially, I'm trying to find out what is the embedding for node V. Aggregating, I'm only looking at the neighbors of V. And when I have already looked at the neighbors of V, I have the aggregated value that I combine with the entry, with the embedding already in V. So this is the neighbors of V combined with its own embedding to concatenate it. Again, there is a learnable weight matrix W and a function which finally gives the embedding of the node V. This is how essentially it works. This is one model, Graph Sage. There are other models. I will again not go into the details of this, where embedding and aggregating and combining happens. This is Graph Convolutional Network. This is Graph, I think, Isomorphic Network. So these are all very interesting new areas where a lot of research can still happen and is waiting to happen. So some applications, very quickly in 2 minutes, I'll go through it. For example, movie recommendation system. Okay, there you see that there are friends in a social network who have watched movies, and these friends may have their initial embeddings. Maybe let's say there are 1 million users in a social network, and let's say I decide that in the system there are 10,000 movies. Each user would have, let's say, an initial embedding in the, I decide that the space, the dimensionality of the space of embedding would be, let's say, 10. So I have 10 dimensional vector initially, and each of these dimensions could be the genre of the movies that this person has watched, the actors, the actor which this person likes because this person has watched a lot of movies, etc. So there could be 10 different measurements which I take, which are of course related to this particular person and the movies watched by this person. So don't think that because there are 10,000 movies in the system, the dimensionality will be 10,000. No, it will be some combination, some information extracted out of the movies that this person has watched, but in a much lower dimensional space, let's say 10 dimensional space. So every node in this 1 million big graph has an initial 10 dimensional vector associated with each node. And then the graph neural network kicks in. It learns the embedding. So initial embedding is whatever initial vector you had given, extracted from the movies watched by this person. And then this, the algorithm starts, and it also takes in inputs from its neighbors. Remember that each node would have different numbers of neighbors, different characteristics of the neighbors. So all this is actually implicitly learned in that weight matrix. And then once the graph neural network is learned, for example, then let's say this person, you look at only in the embedded space, the feature vectors that you now have for each individual. And then you may take the top nearest neighbor in that embedded space of this particular lady here. And you can see that if this particular person has watched some movie X, while her nearest neighbor has not watched that movie X, then you may recommend to that nearest neighbor that, okay, maybe you would be interested in watching X because your friend watched it. And also, you see, it's not just an expert system because your friend watched it, so you watch it. No, the system has learned not only based on the movies watched by the neighbors, but also on different characteristics from the topology of the network. So this question automatically comes, is it as simple as an expert system? No, it is much more than that. So this is a recommender system, polypharmacy side effects, very interesting. You have, let's say, a very complicated graph here of drugs, and drugs interact with each other in the sense that this drug interacting with this drug here, C and D interacting, may give rise to a side effect, let's say R2. C and M interacting with each other would give rise to a side effect R1. Remember that this drug M in isolation and this drug C in isolation may not have any side effects. But when given together, they give rise to a side effect, let's say R1. So these nodes, these edges, the links can have multiple labels because there can be more than one side effect. There can be R1, R2, R3, etc. So links are labeled, links have a particular meaning. Now each drug actually interacts with, targets certain proteins in the bodies. These are known. So you have the level of proteins here, the round nodes are the proteins, and the drug targeting these proteins. Again, we know that proteins interact with each other. So protein-protein interaction happens here. So you see, this is such a complicated network with nodes of 2 different types and the edges of, I think, 3 different types: drug to drug, drug to protein, and protein to protein. So this is a very complicated network. Now the task is, because there could be millions of drugs, there will be, again, a large number of proteins. Now, if you have, let's say, N drugs, it is highly unlikely that you have already tested NC2 combinations and determined what will be the side effects if these are applied in pairs. And as we all know, most of us, especially the aged, take a lot of medicines. So when prescribing a new medicine, the doctor would like to know what are the medicines this person has taken and what are the likely side effects which will happen in combination. So the number of combinations, it's just 2 is NC2, but now you think there will be 3 drugs, 4 drugs, etc. The number of combinations is mind-boggling. So here, the task is, it is not possible to have information of every combination which is there. Can we learn? Can we predict these links? Let's say D and S, there is no information available. Can we predict whether there will be a side effect and what type of side effect will be there? That is where, again, graph neural networks have been used. You can see this is the work here in ISMB in 2018, Zitnik et al. They have explained this work. They have done this work. You can imagine the interestingness of this work and the importance of this work. So with these 2 applications, I will just give you some of the references. Of course, there are more, but just some of the references here. I would like to acknowledge, of course, my student Shucheta, who has helped with the work, who has also taught me a large amount of this particular area. And through my questions, I hope I have also taught her quite a bit. And also Dr. Monideepa Dash, who has joined ISI recently as an Inspire faculty. And of course, I acknowledge DST for a grant for funding, which has helped me in many of my activities. So thank you very much. And just to point out here, if you look at the thank you inside, you can see a face. And that face is the founder of my institute, Indian Statistical Institute, is the face of Mahalanobis. Thank you very much.
Thank you, ma'am, for your enlightening lecture. And if our audience has some quick questions, you can ask. Is there any question, ma'am? Yes. Yes, you can ask your question.
So basically, I have 2 questions.
Okay.
Can you hear me?
We can hear you. Just continue.
Yeah. So first one, I mean, we all know that this graphs, finding features from graph are very difficult. So that's the reason we always use a lot of graph theory, game theory for analysis of link prediction or node. So can we combine both of them? I mean, this graph algorithm along with the graph neural network? This is the first question. And second is, can we use this kind of techniques for vaccination strategies? Like, I mean, COVID is going on, so new vaccination is coming. So when we will plan for vaccination, can this graph neural network be used for that?
Well, both these questions are very open-ended questions in the sense that these are research questions. Yes and no answers are not known. That much I must acknowledge. Combining the graph theoretic algorithms and this approach of embedding, yes, of course, why not? I mean, but very difficult to say immediately how you would do that. But that is, as I said, a research area, a good suggestion, but it has to be thought through. I cannot answer yes and no right now, but I don't see why not. That is a very vague answer to your question. And about the vaccination strategy, again, well, we can, of course, we have to first have a graph. So what is the graph here? The graph could be the population, but then what are the individual human beings? And we have to decide here in such a graph, what would be the edges? Would it be neighborhood? That is where they are living. Is that the graph, or it could be contacts? It's not just neighborhood, because neighborhood has a very sort of less dynamic structure. It is rather fixed in structure, and it's also like neighborhood has almost a fixed structure. But the point is, persons traveling from one place to another place very frequently, that may also come into that graph structure. Yes, so a graph structure, I can see how it can be defined. And then the vaccination, um, again, I don't know, maybe yes, maybe no, I don't know. I cannot see a very straightforward way of doing it right now, because I cannot understand, even if we are able to define the graph, what could be the embedding, what could be the initial vectors that we start with. If we start with the initial vectors, then we can apply GNN and try to get an improved embedding. But what could be that initial, what could be the meaning of that initial embedding is something I cannot right away think of. But this is a question worth pursuing, because the problem is extremely difficult, extremely real life, and affecting all of us. So it is a problem, a suggestion worth thinking about.
Any other question? So thank you, ma'am, for your words, and I would like to request Professor Vishendu Chatterjee to present a small token of appreciation from us to ma'am.
Thank you very much. Thank you very much. It
you.
is it is
For
indeed.
your valuable time, ma'am.
Thank you very much, and also we appreciate this token of gratitude as well. It is indeed. I mean, we hope that this pandemic passes and we are able to meet again, because nothing can really replace person-to-person networking or face-to-face meeting. But thank you very much once again, and really appreciate it. Thank you.
So here we are concluding our first session. So we'll meet sharply at our next session. Technical session will start from 2:30, but the participants are requested to join on or before 2:30. From 2:15, the link will be open, so you can join any time after 2:15. So thank you very much.
সপ্তর্ষি, সপ্তর্ষি, সপ্তর্ষি,
হ্যালো।
হ্যাঁ সপ্তর্ষি শুনতে পাচ্ছ?
হ্যাঁ স্যার, বলুন স্যার, বলুন।
বলছি তাহলে মিটিং এন্ড করে দাও, 2টোর সময় আবার লিংক ওপেন করো। তুমি এখন হোস্ট।
ও আচ্ছা, ঠিক আছে, ঠিক আছে, ঠিক আছে।